All right, welcome to the Explainer. Today we're going to follow the incredible, truly endless journey of water as it moves on, in, and above our planet. This is the story of the hydrological cycle.
Okay, let's just start with a number that kind of puts everything in perspective. 70%. A massive 70% of our planet's surface is covered by water. It's literally everywhere, from the deepest oceans to the air we breathe. It really does define our world.
But here's where it gets really interesting. It's all about the type of water. Take a look at this. A staggering 96.5% of all that water, it's salt water in the oceans. That leaves just a tiny, tiny sliver as the fresh water that most life on land absolutely depends on.
And that distribution right there, that brings us to the core question we're going to unpack today. If we're living on a water world, why do we talk about fresh water being so incredibly scarce and precious?
So, our water droplet's journey begins with, well, a great escape. It has to defy gravity and make its way up into the atmosphere, and it gets its power from the sun.
Now, the main engine for this whole trip is evaporation. Just picture the sun's energy warming up the surface of a lake or an ocean. It gives those little water molecules at the surface just enough of a kick to break free and float away as an invisible gas, what we call water vapor.
And, this process doesn't just happen at one set speed, right? The rate of this escape is influenced by a bunch of different things. Of course, hotter temperatures and more wind are going to speed it up, but if the air is already really humid, that can slow it right down. It's this constant dance of factors.
And hey, evaporation isn't the only game in town. Plants are constantly breathing out water vapor in a process called transpiration. And in really cold places, something amazing happens. Ice and snow can just skip the liquid phase entirely and turn directly into vapor. That's sublimation.
Okay, so let's move on to the next phase. Our water droplet is now a gas, a vapor, floating high above the Earth. It's ready for a ride.
See, that water vapor doesn't just hang out where it evaporated. No way. It gets swept up by these massive global wind currents and gets carried over vast distances. This whole atmospheric transport system is called advection, and it's how moisture from the middle of the ocean can end up as rain hundreds, even thousands of miles inland.
Which, makes you wonder, once a water molecule gets up there, how long does it actually stay? Are we talking hours, days, years?
Well, scientists have actually figured this out, and it's pretty cool. Basically, they divide the total amount of water in the atmosphere by the rate at which it flows in and out. And the answer? On average, a water molecule only spends about 8 days in the sky. It's this incredibly fast turnover that helps explain why our weather patterns can change so quickly. It's pretty amazing.
So after that surprisingly short ride in the atmosphere, gravity calls. It's time for our water droplet to begin its journey back down to Earth.
And this is the part of the journey we're all familiar with. Precipitation. As the air gets colder, that water vapor just can't stay a gas anymore. It condenses back into tiny liquid droplets or ice crystals. They clump together and they get heavy enough to fall. And it comes in all sorts of forms, right? From a gentle rain or soft snow to some seriously destructive hail.
Okay, so the water has landed, and this is where the journey gets really complex. It doesn't just take one path. It splits into this incredible web of different routes, both across and deep beneath the surface.
It's kind of wild, but a whole lot of rain never actually touches the ground. If you think about a dense forest, so much of that rain gets caught on the leaves and branches of the trees. This is called interception, and a lot of that water just evaporates right back into the air, starting its journey all over again.
Okay, so what about the water that does make it to the ground? Well, some of it starts to move across the surface. We call this runoff. And eventually, that water gathers in little channels, which form streams, which form rivers, all of them carrying that water back towards the ocean.
But not all of it just flows away on top. A huge amount of it actually soaks right into the ground. This process is called infiltration, and it's the beginning of a much slower, hidden underground journey.
And once it's underground, that water basically has two main fates. It can hang out near the top, becoming soil moisture that plants can drink up, or it can seep much, much deeper, eventually replenishing these vast underground reservoirs called aquifers.
And then, of course, there's the simplest path of all. Sometimes the water just stops. It gets caught in a puddle or a little dip in the land. Hydrologists have a great name for this: depression storage.
All right, so we've followed one little droplet on its wild ride. Now let's zoom all the way out and look at the big picture. How this entire cycle works as a perfectly balanced global water budget.
So here is the absolute most important thing to get about all of this. We are not getting any new water. The water we have right now is the same water that dinosaurs drank. It's been cycling for billions of years. It's a completely closed system.
So how do scientists and engineers keep track of this precious finite resource? Well, they use a really simple but incredibly powerful idea called the water balance equation. All it says is that for any given area, the water that comes in minus the water that goes out equals the change in how much water is stored there. Simple, but profound.
And they apply this equation to specific areas they call catchments. You might know them as watersheds. A catchment is just all the land that drains water down to a single point, like a river or a lake. It's the fundamental building block for understanding and managing our water.
And all of this leaves us with one final and pretty urgent thought. For thousands and thousands of years, this cycle has maintained a delicate balance that all life on Earth depends on. But now, as our climate changes, things are accelerating. More evaporation, more extreme rainfall. So the big question is, what happens if we finally tip those scales?